Dear students, today we will study Langrange's theorem on subgroups. The order of each subgroup of a finite group is a divisor of order of group. This is the statement of Langrange's theorem. Suppose that G be a group of finite order and order of G be n, and H be a subgroup of G, and suppose that order of H is equal to m, and H1, H2, M are be m distinct elements of H, and for an element of G, HA be a will be a right coset of H in G, and we have right coset of HA will be a set of elements of type H1A, H2A, HMA. Now we prove that HA has m distinct elements. Suppose that any two elements HIA is equal to HJA. From the right cancellation law, HI will be equal to HJ. This is a contradiction because we have assumed that H1, H2, M are distinct elements. Therefore, each right coset of H in G has m distinct members. Any two distinct right cosets of H in G are disjoint, that is, they have no common element. Because G is a finite group, the number of distinct right cosets of H in G will be also a finite. Suppose this is equal to k, and union of these k distinct right cosets of H in G will be equal to G. That is H1, HA1, HA2, HAK are be k distinct right cosets of HA in G, then union of all these right cosets will be equal to G. Now, number of elements in G will be equal to number of elements in HA1 plus number of elements in HA2 plus number of elements in HAK. That is, order of G will be equal to k into m, because in each right coset of H in G, each contains m elements and we have k right cosets. Therefore, order of G will be equal to k into m, because but order of G is equal to n, therefore n will be equal to km. This means k is equal to n upon m, that is m divides n, that is m is a divisor of n. M is the order of H and n is the order of G. This means order of H divides order of G. This is the proof of the theorem, Langrange theorem. And converse of Langrange theorem, if the G is a finite group and M divides order of G, then there is a subgroup H of G such that order of H is equal to M, that is there are m distinct elements in subgroup H. Now, what is index of a subgroup of H in G? The number of distinct left or right cosets of subgroup H in G is called the index of H in G and is denoted by IGH or G colon H. Here k is the index of H in G, then we have m is equal to n upon k, because we have already proved that k is equal to mn. This means k is a divisor of n, therefore index of every subgroup of a finite group is a divisor of the order of group, that is n is equal to mk. We can write it as order of G is equal to order of H into index of H in G. Now we take a very important theorem, very important theorem. If H and K are finite subgroup of G, then order of H K will be equal to order of H into order of K upon order of H intersection K. Because H and K are finite subgroup of G, therefore D, the intersection, is also a finite subgroup of G. Because intersection of H and K is subset of H and also K, therefore D is subgroup of finite group K. The number of distinct right cosets of D in K is also finite. Let A1, A2, AL be L elements of K such that DA1, DA2, DAL are distinct and hence pairwise disjoint right cosets of D in K. Here L is equal to the number of distinct right cosets of D in K, therefore this will be equal to index of D in K from the definition, and index of D in K will be equal to order of K divided by order of D, that is L will be equal to order of K divided by order of D. From the first equation we get HK, the product will be equal to H into K, because K D is a subset of K and D is a subgroup of finite group K, then K will be equal to union of all the distinct right cosets of D in K. Therefore, H can be written as DA1 union DA2 union DAL, that is HK will be equal to H into union of all the right cosets I is equal to 1 to L DAI. This will be equal to I is equal to 1 to L HDA DAI, or we can write it as I is equal to 1 to L union HDAI, and here HD is equal to H because H is subgroup of D is subgroup of H, so HD will be equal to H. This is the union of all the right cosets of H and A, H and G. Therefore, HK is equal to H1 HA1 union HA2 union HAL. Now we prove that there is no two right cosets of H are equal. Suppose that HAI is equal to HIAJ, that implies if these two are equal, then AI AJ inverse belongs to H, also AI and AJ belongs to K, and also AI AJ inverse belongs to K. This means this element is common in both H and K. This means AI AJ inverse belongs to H intersection K, and that implies AI AJ inverse belongs to D. Therefore, DAI is equal to DAJ. But we have already taken that all DAI, DA2, DL are distinct. Therefore, HA1, HA2, HAL are distinct. That is, these right cosets of H and are mutually disjoint. If these are mutually disjoint, therefore order of HK will be equal to order of HA1 plus order of HA2 plus order of HAL, and order of HA1 will be equal to order of H, and this is also equal to order of H L times, because H is subgroup of finite group G, so the order of each right coset of H in G will be equal to order of H. Therefore, order of H will be equal to L times order of H, and here L is equal to order of K upon order of D, that is order of HK will be equal to order of H order of K upon order of D, and order of D, because D is equal to intersection of H and K, therefore this will be equal to order of H intersection K. Hence, order of HK is equal to order of H order of K upon order of H intersection K. Now, Euler's function phi. For any positive integer n, phi n is defined as phi 1 is equal to 1. For n greater than equal to 1, we have phi 1 is equal to 1 and phi n is equal to the number of positive integers less than n and relative prime to n. phi n is the number of positive integers which are less than n and are relatively prime to n. If n is equal to 6, then positive integers then less than 6 and which are relatively prime to 6 are 5 and 1 only. Therefore, phi 6 is equal to 2. There are two elements, two numbers which are less than 6 but relatively prime to 6 are 1 and 5. Therefore, phi 6 is equal to t. If p is a prime number and all the numbers less than p, that is from 1 to p minus 1, are all relatively prime with p, this means phi p will be equal to p minus 1 if p is a prime number. Now, if p is any positive integer, then we can write n as p1 raised to power alpha 1, p2 raised to power alpha 2 and pk raised to power alpha k, where p1, p2, pk are prime factors of distinct factors of n and alpha 1, 2, 3 are powers of p1, p2, pk. Therefore, phi n will be equal to, that is Euler's function phi will be equal to, phi n will be equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 and so on 1 minus 1 by pk. Now, Euler's theorem, if n is a positive integer and a be any integer such that a and n are relatively prime, then prove that a raised to power phi n is equivalent to 1 modulo n. We consider a set G, set of remainders R such that R belongs to Z and R is relatively prime to n, where R is greater than or equal to 1 and less than n. G is a group under multiplication modulo n with the identity element 1. By definition of the Euler's function, G order of G will be equal to phi n. When n is equal to 1, phi n is equal to phi 1 will equal to 1. This means a raised to power phi n, which is equal to a raised to power 1 because phi n is equal to 1, is congruent to 1 modulo 1 because here n is equal to 1, which is true. Now, if we take n greater than 1, then suppose a is equal to n q1 plus r1, where q1 is the quotient and r1 is the remainder. If r1 is the remainder equal to 0, then a is equal to n q1, that is n divides a, and GCD of a n is equal to 1. This means GCD of a n is greater than 1, which is a contradiction. Therefore, r1 is not equal to 0 and r1 lies between 1 and n. Suppose GCD of r1 and n is equal to m. This means m divides r1 and m divides n, and r1, because a is equal to n q1 plus r1, therefore r1 is equal to a minus n q1. By putting this value of r1 in this, that is m divides a minus n q1 and m divides n q1. We can multiply with q1 because m is the divisor of n. Therefore, m will be a divisor of n q1. And from the number theory, from the properties of divisibility of numbers, if m divides a minus n q1 and m also divides n q, then m will divide their sum, a minus n q1 plus n q1. These two cancels out and m divides, this comes out to be m divides a, and also m divides n. This means m divides a n, but a and n are relatively prime. This means m divides 1. This means m is equal to 1. Therefore, GCD of r1 and n is equal to 1. If GCD of r1 and n are n is equal to 1, this means r1 belongs to G. Again, A is equal to nq1 plus r1, that implies A is congruent to r1 modulo n, that implies A raised to power phi n is congruent to r1 raised to power phi n modulo n. Now r1 raised to power phi n is equal to 1 modulo n, because r1 belongs to G, and r1 raised to power order of G will be equal to 1 in G. That implies r1 raised to power phi n is equal to 1 in G, that is n divides r1 raised to power phi n minus 1. Therefore, A raised to power phi n is congruent to 1 modulo n. So, theorem is proved. Next theorem is Format's theorem. If p is a prime number and a is any integer, then a raised to power p is congruent to p modulo a raised to power p is congruent to a modulo p. This congruence function is defined as if a is congruent to b modulo m, this means m divides a minus b. This is the definition of congruent function. First case first, if a and p are relatively prime, if a and p are relatively prime, then by Euler's theorem a raised to phi p is congruent to 1 modulo p. That implies a raised to, because p is a prime number, therefore phi p will be equal to p minus 1. A raised to p minus 1 is congruent to 1 modulo p. That implies p divides a raised to p minus 1 minus 1. Therefore, a raised to p minus 1 will be equal to of type kp for some integer k. By multiplying throughout by a, we have a raised to power p minus 1 into a minus a is equal to a kp. A raised to power p minus a will be equal to a kp, that is p divides p a raised to power p minus a, because p is a factor of a p minus a. This is we want to prove, that is p divides, p is a prime number and a is an integer, then a raised to p is congruent to a modulo p. Second case, if GCD of a and p is greater than 1, and also because p is a prime number, therefore there are only two divisors of p, one and itself p. And if a GCD of a and p is d, it means d divides p and d divides a. Also p is a prime number, this means either d is equal to 1 or d is equal to p. Therefore, GCD of a and p is equal to p. That implies p divides a and also p divides a divides a raised to power p, from the very basic properties of divisibility of numbers. Therefore, p divides a raised to power p, also p divides a. This means p divides a raised to power p minus 1. This is the definition of congruency. A raised to power p is congruent to a modulo p. This completes the proof of the theorem. Students, next we will discuss cyclic groups in the next lecture. Thank you again.